question 6 is a continuation of functions. And actually, this will be the last question that looks at functions. Now, under this question, we are given the function q of x is equals to root of x minus 3. For 3 is less than x and x is less than 7. And also we are given the function p of x is equals to the log of 1 over 3x base 3. Now when you look at this function here, q of x, we can see that it is a root function. So this is a root function. And a root function is really defined by y is equals to the root of x plus or minus p plus or minus q, where the plus or minus p there represents the translations of moving the graph to the left or to the right. And the plus or minus q here will represent the translations wherein we move the graph either up or down. And we know that if our p here, the value of p here is a positive, it means the graph have moved actually to the left. And if our p is negative, the graph has moved to the right. Now, when we have a q that is positive, this simply means the graph went up by p units, and if the by q units, and if q is negative, the graph really went down by q units as well. Now, using that knowledge, we can see here on our graph that this graph actually moved to the right by 3 units because our p there is a negative 3. And you know, another way to view this, if you want to look at the vertical movement, you would see that here we don't have any number added. So we have a 0 here. It's like we have a plus 0 here. So this is like a root of x minus 3 plus a 0. This means the graph didn't go up or down. It is just on the x-axis there. But the other thing to this question is that it has a restriction. This means this graph is restricted. Now, the restriction means that the graph exists only from 3 to 7, and we don't include 7 there. So this is the domain of the graph. These are the values of x. Anything below 3 going down there, the graph does not exist, and anything above 7, the graph does not exist. Now, when we look at the graph of p, you would see that this actually is a logarithmic function. So it's a logarithmic function, a log function. And we know that the log function has a form of y is equals to the log of x here plus or minus p plus or minus q, and we'll have a base of a number there. Now, with this function, we see the same properties. The x plus or minus p here represents our left or right movements, and the q there, plus or minus q, represents the vertical movements up or down. Now, when we look at this specific logarithmic function that we are given, you would notice that this graph actually didn't move left or right, because we actually have here 1 over 3x plus or minus 0 here. So basically there it didn't move. And also outside of these brackets, we have also here a 0 because there's no number there. So it means that the graph didn't also go up or down. So this is to say that our function here would be something that looks like this. It has the vertical asymptote here, and it has the shape that's sitting like this. This will be the function p. And if maybe I were to quickly draw this function as well, the root function here, you would see that it's a function that is on the positive side. So it's half of a parabola. Remember, the root function is a parabola that has been restricted. It's half of a parabola. So this function here would be this one. It will represent this one here, the function that we have here. And it really starts at 3 here, and it ends, so 3 here is included, and it ends at 7, and 7 is not included. So here we have a 7. Now, what I mean by this is that um, this number here, if you put the value of 7 here, it is not defined. You don't get an output value there. So we use this circle here to show that that number there is not included. But this one we shade here, the 3 we shade to show that the graph is actually included. So basically that's what I'm given here. This is how my functions would also look like if I were to really sketch them. Now using this knowledge, we are going to then answer our questions and go to question 6 and look at 6.1. Now, when you look at 6.1, they say here that write down the domain of P. Remember, the domain is all our X values that will give us our Y values. Now, if we look at the domain of P, we can see, and we said that this function P didn't move up or down. And so that means the vertical asymptote is really at 0. So this means this function will really start at 0. It will start at 0 and goes to positive infinity. Or one can say that 0 is less than x and x is less than infinity. Or another way in which one can write this really is to say x is greater than 0. We're looking at the values of x that are above 0, the positive numbers. Now, if you look at the sketch that I did there, you would see what I'm talking about here from the fact that if we start here at 0, where our x is 0, so here where the x is 0, you realize that the function is undefined here because it's an asymptote. It will never cut the asymptote. It doesn't have a point. But if you come above 0, you'll see that the function gives you this point. If you come here, it gives you that point. And if you come here, it gives you that point, and so on. So all these values from anything above 0 and going to infinity there, positive infinity there, that's where our x values will be defined, and that's the domain that we have written. So this is just only 1 mark. It should be really a quick thing to answer. Any of the notations that you use there will give you 1 mark. Now if we go to question 6.2, they say to us write down the equation of p to the power negative 1 for x element of 2 to 0. So we also have a restriction here. And then they say this is the inverse of P, this is the inverse of P. And then they say, right, this inverse in the form of g of x is equals to. Now, if we take our original function P, it is defined by P of x is equals to the logarithmetic of 1 over 3x base 3 here. Now, when we want to do the inverse, the first step that we do is to really interchange x and y, because what we do with an inverse is that we swap the vertical axis with the y axis. We swap them. So that's why we interchange them here. For me to do that, I'll firstly write my p as a y so that it is sitting as a y. Remember, p are the y values. They can also be written as the y values. Now from here, I'll then do my first step where I swap x and y. I'll make my y to be an x and also make my x to be a y. Now when we are at this stage, the second step that we need to do then is to solve for y, is to write this equation in a form of y is equals to something. Why? Because we always write functions as y is equals to something, To do this, we're going to apply the rule where we change the base. Now we have this relationship between a log and an exponent. If you have an exponent, it will be written as a to the power, let's say x, and if you have a log, it will be written as a log of x base a. Now what's happening here is that if you look at both the exponent form and the log form, our a is a base, so this is always a base. Remember, we call this a base in exponent form. We also call this a base in a log form. So when you interchange this, the trick is that you need to go back to this here. So that means in this question, I will then say now that my base will be a 3, and if the base is a 3, so I'm taking this and I'm making it a base just like we did here. So if that is a 3, then we know that this will go back to an exponential function. The x should be at the exponent. And by doing so, you will then realize that the log then disappears because I've addressed these two now here. When the log disappears, and then I'm only left with 1 over 3y. So it means here I'm going to have 1 over 3y. And to solve for y, I'm going to times both sides really by a 3. I'm going to multiply both sides by a 3 so that this 3 and this 3 cancels, and this side I'm going to have a 3 multiplying this here. So this means my function will then end up being a 3 to the power 3 multiplied by a 3 there. Then this can be my final answer, or sometimes one may want to further simplify this by keeping the base here and adding the exponents, in which case I'm going to have a base of 3 and I'm going to add my exponents, which is going to be x plus 1. Now remember, the question requested that we write this function in the form of g of x. So it means I'm going to say this is the same as g of x is equals to a 3 to the power x, or it is also acceptable to actually simplify further and leave it at 3 plus 1. Both these two functions are the same. And what this function is really telling us is that we have an exponential function which has been shifted to the left by 1 unit. Now this question really will give you 2 marks for it. So what we really get marks for here is the fact that we were able to interchange our x and y, and then we simplify to get to that final answer. Now the next question is going to be question 6.3, which says determine the equation of f. So f is a new function. They say this is the reflection of q about the line y is equals to x. Now if we do a reflection about the line y is equals to x, it means we are actually doing an inverse. So this is another way of saying find the inverse of the function q, because we're looking for the inverse of the function q. That's another way of saying that. Because remember, when you reflect a line about the line y is equals to q, you actually swap your x's. Your x becomes y and your y becomes x. And that's a definition of what an inverse is. So this means here I'm going to take the function q that we have here. So we are under 6.3. I'll say the function q of x, which was defined by x minus 3. And this function, remember, it was defined for 3 is less than x and is less than 7. So there's this restriction, remember, that's the domain. Now we're going to do the same thing because it's an inverse really. We're going to firstly write this in a form of y. We're going to change our q to y because q is a value of y. It represents the output values. And here I'm going to have x minus a 3. Then following this, I'm going to then interchange x and y. I'm going to swap x and y because I'm reflecting this across the line y is equals to x. I'm changing my x's here. Now this would mean that here I'm going to have an x, my y will become an x, and I'm going to have a root of y minus 3. And from here, as usual, we would want to then solve for y. So we want to write our function in a form of y is equals to something. Now to do that, I'm going to really square the left hand side, and because I'm squaring the left hand side, I should also square the right hand side. So what you do on the left, you do on the right. When we square this side, you would see that the root and the 2 would cancel each other out, and here I'm going to have an x squared. So this means here I'm going to have an x squared is equals to y minus a 3. And at this stage, I'm simply going to have my negative 3 to come this side, so that I now have x squared plus a 3. And this will be the function in a form of y is equals to. But remember, on the question, we're looking for the equation of f. It means this function, after reflecting it about the line y is equals to x, it becomes a new function f. So that means we are going to write this function in a form of f of x is equals to the x squared plus 3x. And this makes sense really because, you know, when you look at this function, it's a parabola, right? It's a quadratic function. And we did say here when we interpreted the question that a root function is actually a parabola that is being cut so that you have one side of it. Now that tells me that we have to then bring again this restriction on this function because, you know, this function is chopped It only exists for a given domain. Now, our restriction will be really simple to find. We will say this function is defined for. Now, we are going to use this original function to find the corresponding y values. So I'm going to put a 3 here to find the y value, and I'm going to put a 7 here to find the y value, right, the corresponding y values. So what I'm doing here is that I'm trying to say, if I put a 3 here, what is the y value? If I put a 7 here, what is the y value? Now this y values will be my domain, because on the new function, this y-axis becomes the x-axis, so it's going to be my domain for the new function here, which is a parabola that has been chopped. So now I'm going to then say here I'm having a root of 3 minus a 3, and you can see that the root of 3 minus a 3 gives me a 0, and this means I'm going to get a 0. It means my y value is 0. Now this y value that we have for this function will be the x value on the inverse. So that means here I'm going to have a 0 is less or equals to x. And now I'm going to then do the same thing by putting here a 7 minus a 3. A 7 minus a 3 should really give me a 4, and the root of 4 we all know that is a 2. So this means that my y value here would be a 2, and the y value on this inverse becomes the x value. So that means this graph will then have to end there at 2. That would be the restriction for it. And that's pretty much what we do. So what I'm saying is that here we get a 0, here we get a 2, and now these values 2 and 0 and 2, they are now on the x-axis. So we're going to have a 0 here and a 2 for this function that we have, which will look like something like that, because it's an inverse now. I hope that's clear and it makes sense, and this really is only for 2 marks. So here definitely you'll get a mark for swapping your x and y, and getting to the final answer. There isn't much simplification that we do here. Now when we jump to the last question, it really says to us here that on the same set of axes, using the same Cartesian plane, right, draw the graphs of f and g. Now the graphs of f and g are both the inverses that we found on the previous question. So I'm drawing the inverses of those functions. Now if you look at the first one, we have in 6.4 here. So before I actually look at them, I'll just construct quickly my Cartesian plane. I'll say this is x, this is 0, and this is y. Now the first graph that we're going to look is that of p, that of g actually, where we found the inverse here. If you look at this graph, really is just a regular exponential function that will move like this. It's just a normal exponential function that will move like that. But there is also a restriction here that actually I didn't include on this question here, and it's very important because we're going to get marks. So remember, they restricted this function from 0 to 2. So here we have to put this restriction when we write our answer to get full marks. So here it means you have to write a statement to say for x an element of 0 to 2. 0 to 2, yes, 0 to 2. So it means now this function only exists on the domain of 0 to 2. That means after drawing this function here, I actually have to say here at 0, when x is 0 here, I get a number there, which is going to be a 3. And these numbers are included. And this side of things, the graph does not exist. Let me reduce my eraser here. This side of things, the graph does not exist because it is only beginning at 0 here, and the number that we get here of 3. Because remember, if you put a 0 on this function here, if we put a 0 here, I'm going to have 1, then 1 times 3 is just a 3. Or you can put a 0 here, you're just going to have a 3. So that's what I'm saying, it only starts at the point 0 and 3 here. And this graph will go on like that until it gets to 2, because it's restricted until 2 here. So somewhere here on 2, this is where the graph will end. And actually now that means I'm going to chop it again here, and this graph will actually be such that it's an open circle there, because we're saying 2 is not included, it's not part of the function. If you put a 2, you don't get a number there. So that's how my function would look like. Maybe I can adjust this shape so that it looks nice, because it looks like a straight line now here. So maybe I can sort of adjust the shape to, make sure that it's a curve like that. Now the second graph is a parabola. And with this specific graph, maybe I can use a different type of color just to differentiate these two graphs. You will see now here that with the parabola, it also begins at 0, meaning if you put a 0 here, what do we get there? We also get a 3, because if you put a 0 here, we're only left with a 3. So we get the same point, and it is included as well. So that means this point here, that's where the graph will begin. And it then ends at 2. So it will end at 2. But now if we put a 2 here, we're going to have a 4. And 4 plus 3, that should give us a 7. So that means this graph will be mapped up to a 7. So here I'm going to have a point 2 and a 7. So it means somewhere here I'm going to have a 7. So this is the point that I'm going to have. And this again it's sort of a parabola that should be looking like this, but it only exists on this part. So it means the other parts I'm going to cut them up. It's a root function that is being only reflected on this part here. So this here is a 3. So this point here, I'm having a point 2 and a 7. Maybe we can check what this number is here. And we can quickly do that. If we put a 2 on our exponential function, so if we put a 2 here, I get a 9 there, and the 9 times 3, that should give me a 27. So this means on this point here we have to get a 27 here. So this is 27 here, and that's all you need to put on this graph. It's very important to highlight these points here to say this is a 7, this is a 27, this is a 0 and a 3, and also 0 and 3 for both graphs. And your 3 marks really will come from there, where we will mark 1 mark for the correct shape for each graph and also its restrictions, and the other mark will it will be a mark that covers these points here for both those graphs. And that's how you get your 3 marks. Very simple question, I think, this one. It requires you to know knowledge of inverses and also how to restrict graphs. Be comfortable with playing around that.